Chapter 5, one step calculation number 3 says calculate the resultant of a horizontal vector with a magnitude of 4 units and a vertical vector with a magnitude of 3 units, which means that what I just said about the quick way, that's not going to apply here because they're of different lengths. Okay, so here I have 4 units, here I have 3 units, and I put them tip to tail. There we go. And the resultant vector is this one. And now I figure what it is. And write that the resultant is the square root of 3 squared plus 4 squared. I always like to write the square root last so I know how big I have to write it. You can do that on the calculator. You can do it also in your head, because you're going to get 9 plus 16 square root of 25, 5. And by the way, if I tried this by measuring, I come up here with 3 units on this vector. In the vertical, I do have 4 units. Of course, that's what the squares are telling me. And then here, I indeed come up with 5 units. Chapter 5, problem or OSC, one-step calculation number 4. And it says, calculate the resultant velocity of an airplane that normally flies at 200 kilometers per hour if it encounters a 50 kilometer/hour wind from the side at a right angle to the airplane. So this one here is the 200 kilometers per hour, and that's my scale. And then this one here is the 100 kilometer per hour crosswind, and when I put them tip to tail, again, so each 50, I mean that's the 50 kilometers per hour crosswind, so each square would be 50, and then the resultant would be tail of the first one to tip of the second one. And I'm gonna use this one here and rotate it, and let's see, slightly more than 200. Well, when I do it with the Pythagorean theorem, I'm going to come up with that the total velocity of the airplane is going to be 200 kilometers per hour squared. I'll leave out the units here because I don't have enough space. 50 kilometers per hour squared. Take the square root. When I do that on the calculator, it's going to be square root of 200 squared plus 50 squared. And I come up with 206, and that's exactly what I had measured. 206 kilometers per hour. The next problem is chapter 5, problem 2. It says, if you stand next to a wall on a frictionless skateboard and push the wall with a force of 40 newtons, how hard does the wall push on you? And if your mass is 80 kilograms, what is your acceleration? So you're pushing onto the wall at 40 newtons. Well, the wall is pushing back on you. I put this in a different color, in the opposite direction with the same force of 40 newtons. That's of course Newton's third law, equal and opposite forces, and that's what I had mentioned a couple of times before. There's really no calculation involved, which is why you see mostly Newton's second law calculations. So here's that. It says that, does it say a boy in here? If you stand, okay, so you would have to have a mass of 80 kilograms, 176 pounds. That would be nice for me. So probably not this boy here. Any case, you would use Newton's second law, force equals mass times acceleration, or acceleration equals force over mass. 40 newtons divided by 80 kilograms equals 0.5 meters per second squared. And that's how fast you or the boy would accelerate, as long as you are exerting that 40 newtons on the wall, and the wall in turn exerts 40 newtons on you, which might be just for a second or so. So for that time you have that acceleration and it gets you some speed, and once you're off the wall, well, you're not accelerating anymore because you're not pushing anymore. Okay, chapter 5, problem 4. Forces of 3.0 newtons and 4.0 newtons act at right angles on a block of mass of 2.0 kilograms. How much acceleration occurs? So here we have this force acting that way and that force acting this way. In order to calculate, we have to put them tip to tail. And then of course my scale was, this here would be 3 newtons and this is 4 newtons, and the resultant would be this one here. We actually had that earlier. So 3.0 newtons, 4.0 newtons, and the result comes out to 5.0 newtons because we did that earlier. 3 squared plus 4 squared is 25. Take the square root, that's 5. However, they didn't ask for force, they asked for acceleration. But I calculated that for a reason, because in order to determine the acceleration, I need the force anyway divided by the mass, which I almost forgot is given in the problem. That was 2.0 kilograms. So the force of 5.0 newtons divided by 2.0 kilograms comes out to 2.5 Newton per kilogram, or meters per second squared. Again, here on the side, when I come up with Newton kilograms, that's the same of saying kilograms meters per second squared. That's the Newton, and this would be Newton's second law. Force equals mass times acceleration. And now I divide that by actually the mass, the kilograms, and that's why these two divide, and Newton over kilogram is the same as meters per second squared. But I had mentioned that in the previous problem.